right, welcome everyone. So what we're going to be doing today is we're talking about thermodynamics. So thermo, we know that the stem of the word thermo, just like in thermometer or in thermostat, is referring to what? Heat, perfect, and energy. And so we're just talking about thermodynamics, and we already talked about thermochemistry at the beginning of the year, but we're going to talk about three major things now. What we talked about at the beginning of the year was we focused on delta H, and we focused on enthalpy, and whether a reaction was exothermic or endothermic. And now what we're going to be talking about is we're going to be talking about a couple of the other laws of thermodynamics. So the first law of thermodynamics was what we talked about back at the beginning of the year. And the first law of thermodynamics states that the energy of the universe is what? Constant. Awesome. So we know that the energy of the universe is constant. And now the second law of thermodynamics states that the entropy of the universe is increasing, which means that what's happening, it's becoming more and more disordered. Perfect. It's becoming more disordered. And so we know that at the beginning of the week, if you start off with a clean room, over time, what happens to your room? It gets messy, okay? And that's the way that nature basically goes. And so it's this whole idea of inflation, okay, moving out. So now we've got the third law of thermodynamics as well, which is very, very specific. And it says that the entropy, or the amount of disorder, of a pure crystalline substance. So if you have a crystal, a pure crystal, and you're at 0 Kelvin, which is a temperature that we've attained, yes or no? No, that we've not been able to attain is what? 0. Okay? So the idea would be that if you could figure out the entropy or the amount of disorder of a pure crystalline solid, if you're at 0 Kelvin, nothing is moving, everything is perfectly organized, okay? Then the amount of disorder would be equal to 0, and that's the third law of thermodynamics. So let's first talk about this word spontaneous. Spontaneity, all it means is a reaction will proceed in the direction written without the addition of outside what? Energy. Awesome, that's it. So without the addition of outside energy. That's all it means to be spontaneous. So you can have a spontaneous reaction that's actually really slow. It does not tell you anything about the kinetics. So that's a big misconception, is people think if it's spontaneous, it's fast. It actually doesn't tell you anything about the speed. You can have a spontaneous reaction that takes millions and millions of years to happen, as long as it doesn't need any outside energy for it to happen. So, two things determine spontaneity. One thing is your enthalpy, which we use what symbol for enthalpy? Delta H. Awesome. So delta H, and entropy, which is delta S. Okay, so those two things are used to determine spontaneity. But spontaneity does have a specific letter, and the letter for it is delta G. And they call it Gibbs free energy. And if you know what your delta G is, you actually could tell whether a reaction is spontaneous or not. But if you're given delta H and delta S, you need to look at both of these together. You cannot tell, and this is a great multiple choice question that I've seen over and over again, is they'll say a reaction is exothermic. Is the reaction spontaneous? And one of the answers will be that there's not enough information that's provided, okay? So you have to actually know about the entropy as well. Or same thing with the entropy, you can't tell unless you know the delta H, all right? So we'll talk about what are the exceptions to that, because there are exceptions where if you know that the entropy, one of them can trump the other one. So you could have an endothermic reaction and have a whole bunch of disorder, and then you can get a spontaneous reaction. Or your reaction can be very, very, very exothermic, and your disorder is actually decreasing. So maybe a gas is turning into a solid, we'll talk about this now, and you could still have a spontaneous reaction. So it can be trumped by one of them. If one of these is really high, then it can trump the other one, okay? So let's first review enthalpy. So it's a measure of the energy absorbed or released in a chemical reaction. And what are our units? Well, we remember this. Our units were kilojoules per mole. Awesome. Our units were kilojoules per mole. And remember, we said that elements in their standard states have delta HF that's equal to 0. Okay, so if it's in its standard state. Delta S, or entropy, is a measure of the randomness or disorder of a system. Well, let's take a look at the units of this. So I'm just going to pull out the thermo chart for just a second here. And so we have our delta H, and we said our delta H was in kilojoules per mole. So we had that chart that we use, like aluminum solid was 0 and barium solid was 0. Now let's take a look at entropy, which is S here. And if we look at our entropy, we can see that elements that had, like aluminum solid, that had a 0 in their enthalpy, do not have a 0 value. So when is entropy equal to 0 again? Only when what? It's the third law of thermodynamics. It's only when you're at 0 Kelvin. Only if you have a pure crystalline solid at 0 Kelvin, then your entropy would be 0, okay? And so this is at 25 degrees Celsius, and so you can see that we're not getting any zeros in this case. What are the units of it? Joules per mole Kelvin, and that's a problem because we're going to be merging these delta H, delta G, and delta S into one equation. And so you have to be careful. Delta S needs to be converted so that it's in kilojoules so that our units match before we do the calculations. So this is joule per mole Kelvin. Let's go back to this. And we've got joules per mole Kelvin. And again, the reason why I put stars here is you need to convert to kilojoules before you use it, which means if your unit is getting bigger, your numbers should be getting smaller. And then, so if we want our unit to get bigger, then we're actually going to shift it 3 positions to the left before we use it, okay? And then delta G is Gibbs free energy. This is how much energy is available. How much energy do you have available? And that's why it tells you the spontaneity. And so will the reaction proceed in the direction written without the addition of outside energy? And the units of this are the same thing as delta H, and it's kilojoules per mole. Okay, so the equation is called Gibbs, and I say that Gibbs likes to wear hats, okay? Because you're going to get your H and then your temperature, delta S, and so there's your G, there's your H, there's your T, there's your S, and so this was the picture here of Coach Gibbs of the Redskins wearing his hats. And so it just happened to be that he does always wear hats. I didn't do this for real, he really does. Okay, so it's a good way of getting the equation down. This is one of the equations that you get on the equation sheet anyway, okay? But a good one to know. So here's another thing that goes along with this that is really going to help you a lot. Sara Eats Gross Ham, okay? Sara, delta S, you actually want to be positive, okay? And E, which we're going to talk about electrochem next, your EMF, you actually also want your EMF, your cell's potential, you also want that to be positive, okay? So those two being positive would mean that you have a spontaneous reaction. So all of these that we're doing here would mean that your reaction is spontaneous, okay? For delta G, you actually want delta G and you want delta H to both be what sign? Negative. You want those to be negative, and that would also tend to favor a spontaneous reaction. But again, delta S and delta H, you cannot use alone. These two, you have to use with each other in order to tell whether a reaction is going to be spontaneous or not. So you can't tell if it's going to be spontaneous. Like with delta G, if it's negative, it's automatically spontaneous. Same thing with your E. If you know your E and it's positive, which again we'll talk about later, then you automatically know it's a spontaneous reaction. It's going to proceed in that direction as written without the addition of outside energy. But these two have to go hand in hand. All right. So we're going to talk a little bit more about this equation in just a little bit. So let's review the enthalpy. So remember how we would do moles of the products minus moles of the reactants? Well, you multiply your moles of the products and then subtract your moles of the reactants. So this is a measure simply of the energy either absorbed or what? Or released, yep, during a chemical reaction. A chem reaction. Okay. So an important point is that a reaction may actually absorb energy as an endothermic reaction and still be spontaneous. I was talking about that before. For example, water going from solid to liquid is very spontaneous. It's a spontaneous reaction, but it's endothermic, meaning that delta H is actually positive, which if you looked at a delta H being positive, you would say that's not going to be a spontaneous reaction. But again, you don't know unless you know the entropy. So it says you must consider entropy as well. And water going from a solid to a liquid is actually increasing in the amount of disorder. So going from, and that's what we're going to talk about next, this is actually increasing in delta S or disorder. Okay, so solids are more ordered than liquids, and liquids are more ordered than gas. So the gas would be the highest or most positive delta S. So when delta S is positive, randomness is what? Or disorder is increasing. Okay, it's increasing. So the more disorder that you have, like the gas phase, the greater the entropy. So if we had a solid that was in a perfect crystal, okay? So if we had a perfect crystal of a solid and our atoms were all at these points of a crystal, then this part here is less disorder, or is, least amount of disorder. Whereas if you have gas and you just have a whole bunch of gaseous molecules that are kind of all over the place, then this side here has the greatest amount of entropy, in other words, the most disorder, and so our delta S is going to be the most positive when you're talking about having lots of gas. So let's predict the sign of delta S here and see if we get this, okay? So in this case here, delta S is, if we're going from a liquid to a gas, is it becoming more disordered?
Yeah.
Yes, so we would say that delta S is positive. Okay, let's do the next one. We've got a solid, and then it turns into a solid and gas. So is it becoming more disordered? Yes, so that would also be positive. Next one, we've got gas, and here we have 2 plus 1 is 3 moles, but now we're forming 2 moles. What do you think? Less disordered. It's becoming more organized. So this would actually be negative. Next one, we've got solid, gas, all going to solid. That one would also be negative. This one is becoming less disordered. It's very confusing because it's the opposite. It's becoming more disordered. So the fact that we're using the word dis in there kind of throws people off. So the more disordered it is, the more positive it is. Okay? The more disordered, the more positive your delta S. And then in this case, we've got solid and gas, and then we also have solid and gas. And it's hard to tell on this one. I'm going to say question mark, is it at equilibrium already? Okay? It looks like it may actually be at equilibrium already, and there may be situations where you get something like that, where they pretty much look like the disorder is pretty much staying the same. You would say that there really isn't a change in your, there is no delta S. Okay? All right. Delta S is calculated the same way as delta H. The only things to keep in mind is elements in their natural state do have an entropy value. We talked about that already. So like the delta HF for oxygen is 0, but the delta S does have a value. And again, we said that entropy is measured in joules instead of kilojoules, so we have to convert before we use it. So let's try this out. We're going to do products minus reactants, so same as what we did before. So we're going to start on this side, and we're going to say our delta S is equal to 2 times SO2's value. So we're going to come here and get the value from the chart, and it's 248. Add your other product, so plus 2 times our NiO, which is 38. And then your reactants you're going to subtract. You can either get the sum of them subtracted, or you can just subtract both of them. That's what I usually like to do. So minus 2 times the NiS, which is 53, and then minus again, because it's another reactant, 3 times the oxygen, which is 205. And then we're going to plug this all into the calculator and get our answer. All right, and you should get negative 149. The only problem is this is joules per mole Kelvin. We want kilojoules, so what do? Shift your decimal 3 loops back. So we're going to go 1, 2, 3. Again, if our unit is getting bigger, our number should get smaller. So negative 0.149 kilojoules per mole Kelvin is what our answer will be. And then if you need to use it in the delta H or the delta G equation, then you can do that. All right, let's go to the next page. All right, and free energy. So now let's talk about delta G. Gibbs free energy, this is simply a measure of what of your system? What do you think? Spontaneity. Awesome, that's all it is. It is the spontaneity of your system. Perfect. Okay? And it's the maximum amount of energy that's available from a chemical reaction. So a negative delta G, we said that our saying, everybody say it, Sara eats gross ham. You want delta G to be negative. So gross and ham, you want negative. Sara Eats, those are positive, those are good things, but gross ham is going to be negative, okay? So this is negative, so in this case, you do have a spontaneous reaction. And that means when we say it's spontaneous, your reaction is going to go reactants toward products in the direction written. Positive delta G, then that means it's non-spontaneous, and instead, the reverse reaction would be spontaneous. Got it? So if it's positive, that means that going backwards would actually be spontaneous. If delta G is equal to 0, then your system is at what? Equilibrium. Awesome. And it says there's no driving force for the reaction to go in either direction. It's just going to sit there. So question 3 says, predict whether the following will be spontaneous, discussing temperature. So rewrite the equation here for Gibbs free energy. So delta G is equal to what? Delta H minus T delta S. Awesome. So if our delta H is negative and our delta S is positive, well, that means it's exothermic, and that means that it's increasing in disorder. Well, both of those are favorable, right, for spontaneous reactions. So we would say that delta G is always spontaneous. No matter what the numbers are, it will always be spontaneous if you have a negative positive. Okay? So your randomness is increasing and you're releasing energy. If your delta H is positive, meaning it's endothermic, and your delta S is negative, meaning you're decreasing in disorder, then in this case, what's true? Never spontaneous. Awesome. This is never spontaneous. Okay? So now, what if it's positive, positive? Well, this is really easy to remember, okay? We're going to say that delta G is only spontaneous, and this is really high, this is really easy, at high temperatures, okay? And the reason why this is easy is because you'll go positive, positive, and for high, we're going to say positive, okay? Like a really high temperature. And the reason why is, if this number here is positive, and this number here is also positive, which we want this number to be positive, and this temperature is so high that this overtakes and exceeds that T delta S is greater than delta H, so in other words, T delta S is greater than delta H, then your negative is going to take over. You're going to have a bigger negative number, so in other words, your negative is more than your positive, then your delta G will also be negative. Okay, so mathematically that works, but you can just memorize that. So the idea would be positive, positive, high. Okay? So then if it's negative, negative, then guess what that is? It's only spontaneous at low temperatures. Only spontaneous at low temperatures. And so we're going to say minus, minus, low. Okay? So positive, positive, high, negative, negative, low. And in this case here, your delta H is actually going to be greater than your T delta S. And if that happens, then we will still be able to get a spontaneous reaction in that case. Okay? So this is something that you'll end up wanting to make sure that you really remember, that you memorize. So if it's a negative delta H and a positive delta S, you know that for sure. If you write Sara Eats Gross Ham, that might help you a lot. So again, just rewrite it yourself now. So Sara Eats Gross Ham. And Sara Eats are both what? Positive, positive. And gross ham are both negative, negative. And this is what gives you a spontaneous reaction. Okay, that's in favor of a spontaneous reaction. Got it? Okay. So here's a really important thing, because this is something that shows up often either on free response questions or multiple choice questions. And the thing is, during a phase change. If you have a phase change, one question may ask, what is delta G during a phase change? Well, during a phase change, we know that our temperature is remaining constant because all of the energy is either getting used, well, in that case, is getting used to do what? Change the phase. Otherwise, your energy would be used to pull apart the molecules. All of your energy at this point is being used to change the phase, which means you have no free energy. There is no free energy. So during a phase change, guess what delta G is equal to? Zero. Okay? There's no free energy available. It's an easy way to remember it. So as long as you say during a phase change there's no free energy, my delta G would be equal to 0. Well, the question is what happens to the equation? Well, what you can do is they may ask you for the boiling point of a substance, or they may ask you for the melting point of a substance, and it makes the equation really easy because you work out delta G equals delta H minus T delta S, and you're looking for the boiling point or the melting point or something like that. And you can calculate this because if this is equal to 0, then your equation just becomes what? Delta H equals T delta S, but you want T alone, so what would you do? Divide by delta S to the other side, and your equation becomes T equals delta H over delta S, and you can actually get the boiling point, for example, of a substance that way. Because sometimes you'll look at a problem and go, what? I'm so confused. How am I supposed to figure out the boiling point? I have no equation that can give me that because I have two unknowns. But if you know that during a phase change your delta G is equal to 0, then you only have one thing in there, and it would be your temperature that you don't know, instead of having two unknowns. So this says, and we'll do a problem like that. Calculate delta G at 298 Kelvin for the following reaction to determine whether the reaction is spontaneous or not. Okay, so let's go ahead and plug in our equation. So delta G is equal to delta H minus T delta S. They're telling us our delta H is negative 393.5 kilojoules per mole minus T delta S. So they give us our temperature right there. It's 298 Kelvin. Now, we have to be careful because this is in joules. I cannot plug it into this equation unless it's converted. So how do I switch it? 3 to the left. Awesome. So go 1, 2, 3 to the left. And right here, I'm just going to do it in the beginning. I'm going to write 0.00305 kilojoules per mole Kelvin. So that's what we're going to write down in here. You cannot change it after. You cannot do it after you've already done this calculation. You have to do it before you subtract. Okay? Otherwise, your order of operations is all wrong on there. So that's kilojoules per mole Kelvin. Go ahead and plug this into your calculator. Okay, and we should get negative 394. Stop right at 394, and our unit is what? Kilojoules per mole. Awesome. And I forgot, this was Kelvin, so our Kelvin's going to cancel out. Our temperature cancels out, unit. So we end up with kilojoules per mole. Spontaneous or not? Delta G is negative. If delta G is negative, is that spontaneous? Yes. Awesome. So that means that our reaction is spontaneous. Is there a way to tell before we even did this problem? How?
Negative, positive.
Delta H is negative and delta S is positive. That means it's always spontaneous. Okay, so negative, positive, that works anyway. We would have been able, if this was a multiple choice problem and that was the only question, we would have been fine right there. Okay, so now let's try this next one. Bromine is going from a liquid to a gas, which means what's happening to bromine? It's boiling, it's vaporizing, or boiling. And what's the big thing about that? Delta G is equal to 0. So just keeping that in mind, just in case they ask us a question about that. So the first question is entropy increasing or decreasing for this phase change? We're going from a liquid to a gas. Is it becoming more disordered?
Yes.
Yes. So you would say that delta S is increasing, meaning the sign is positive. Perfect. Our delta S should be positive, which it is, so we know it's increasing. So it's increasing, right? And then it says, what is the boiling point? Oh, there we go. What is the boiling point? Okay. So we want to know what the boiling point is, so let's write our equation. So delta G is equal to delta H minus T delta S, but we're going to make this 0. So you can either plug it in now or after. Remember what we ended up getting up there was, we said that delta H was equal to, so we could just do T equals, we could add it to the other side. T is equal to delta H over delta S, right? T is equal to delta H over delta S. Okay, so now let's plug in what we know. Delta H is equal to a positive 31 kilojoules per mole. And what do I need to do to my S?
Kilojoules.
Switch it to kilojoules. Good. So 1, 2, 3 to the left. So that gives me 0.093 kilojoules per mole Kelvin. So we're just going to divide 31 divided by 0.093. And what did you get? 333?
Yep.
And our kilojoules per mole cancel out. Okay, that all cancels out. And if you divide by Kelvin, then that means that you're going to get per Kelvin. Then, so per Kelvin means that you just get Kelvin. So we've got 333 Kelvin is our answer. Good? All right, and down here, all this is it's asking us to calculate delta G. It's the same exact thing that we're doing before, okay? So let's set this problem up real quick here. So same thing, we're going to do products minus reactants just like we did for delta S. So 2 times, what you should get is negative 1378. And our units, if this is delta G, then it should be kilojoules per mole. Now, when we say per mole, though, we're talking about a reaction here. And so that's a little bit hard because it's not really per mole. It's per 2 moles of methanol, and it's per 3 moles of oxygen. So I'm just going to say kilojoules because it's for the reaction, unless I specify which one I'm talking about. So I'm just going to say kilojoules on that, okay, and not say kilojoules per mole. All right, and last thing on this page here, too. Now it's asking us to find delta G, delta H, and delta S. And so first thing we have to do is we're going to need to use our equation to figure out delta H and delta S, and then we can use the Hat's equation. Okay. So what we have here is we figured out our products minus reactants for our delta H. We figured out our products minus reactants for our delta S. Again, keep in mind, before we use this, we need to switch it to what? Kilojoules. So we're going to go 1, 2, 3 to the left. I'm going to do it now so I don't forget. So it's negative 0.187 kilojoules per mole, in this case, mole Kelvin. So now let's do our delta G. Delta G, again, is equal to delta H, which we found out right here, which was negative 198 kilojoules, minus our temperature. They tell us it's 25 degrees Celsius. What do we have to do to that? Add 273, so we get 298 Kelvin, and then times our delta S, which we figured out was negative 0.187 kilojoules per mole Kelvin. So go ahead and try to, all right, and what you should get is negative 142, and again, we've got kilojoules, this was per mole, kilojoules per mole in this case. Okay, and the last thing is free energy and equilibrium and how they're related to each other. So delta G also conforms to Le Chat, okay? And so it does conform to Le Chat's principle. And we know that if we're moving in this direction from reactants to products, do you remember if your products are greater than your reactants, we said that K was what? Greater than 1. Awesome. And if you're favoring your reactants, then we said that K is less than 1. So, if delta G is negative, then we would say that K is greater than 1 and the reaction is spontaneous, meaning we're favoring the products. If your delta G is positive, then K is actually less than 1 and the reaction is non-spontaneous, favoring the reactants. And again, the reverse reaction would be spontaneous. And if delta G is equal to 0, then K is what? Equal to 1. And so we would say that the reaction doesn't favor either side, but remember, the reaction does not stop. It simply is there's no net change anymore. And this last thing here, all this is if you want to know the direction of a reaction, then we can use this equation. We know what R is, and R, because we're using joules and kilojoules, anybody remember what the R was in joules? 8.31. But we don't want it in joules per mole Kelvin. Instead, we want it in kilojoules. So what would it be? Which one would we use? 0.00. So shift it 1, 2, 3 to the left. So 0.00831 kilojoules per mole Kelvin is what we're going to use for our R. Okay. Q. What is Q? Do you remember? It's simply when your concentrations are random. Awesome. And so Q is simply equal to concentration of a products over concentration of a reactants, but that's when you're not at equilibrium. Not at equilibrium. So as long as you're not at equilibrium, then that means you're talking about Q instead of K. So in this case here, you can use K if you are at equilibrium. You can use Q if you're not at equilibrium. So at equilibrium, you could also use one of these equations. And so you're just plugging in your values if you know your concentrations at equilibrium. So let's try question 8. Calculate delta G for the following reaction if they're giving us pressure values, okay? So they're giving us the pressure values of these substances. And remember, when you do equilibrium, you do not include solids or liquids. Awesome. So let's work this out, and they're giving us our delta G values, but this one is 0, and this one is also 0, and this one is negative 16.6. So our delta G is simply equal to products minus reactants, so it's really just 2 times negative 16.6 kilojoules per mole. And so 16.6 times 2, we get a negative 33.2 kilojoules per mole. So that's our delta G. So now what they're doing is, this is our standard delta G though. Okay, we haven't seen this before, but that's from our chart, from a table, that's our standard delta G. And now what we want to know is, we want to know what delta G is if we have random concentrations and it's not at equilibrium. So what we're going to do is, we're going to use one of these equations. Well, because we're not at equilibrium, guess which one we're going to use? The one with Q. So let's write our equation out. Delta G is equal to standard delta G plus RT ln of Q. All right? So we know our standard delta G, we just figured that out, was negative 33.2 kilojoules per mole. Then we're going to add, what R do we use? 0.00831 kilojoules per mole Kelvin. And then we're going to multiply that by our temperature, and our temperature is 298 Kelvin. And we're also going to multiply it by ln of Q. So ln is just your natural log button on your calculator. And now we need to do Q. So let's write what Q is equal to. We know it's products over reactants. And so in this case here, our equation is NH3 is our product, but what do we have to do to it? Squared. Awesome. Nice. Divided by N2. And remember, this is pressure. I'm doing concentration, but you would be writing pressure in this case. So it would be P if I corrected this, times H2 cubed. Okay, so it really should say pressure of each one of these. So now let's plug it in. Well, we know that our NH3 concentration, they tell us, is 1 atmosphere right here. So it's 1 squared divided by our N2, which is also 1 atmosphere. And our H2 is 3 atmospheres, but don't forget to cube it. So what's our Q equal to? 1/9. 1/9, 1 squared, and then we want a number that we can plug into here, divided by 3 cubed. And we get 0.0, what do you get? 0.037? Yes?
Yeah.
Okay. So this answer is 0.037, and so that's what goes here, is 0.037, and there are no units. Remember, there are no units. And what you should get is negative 41.4, and in this case, we're talking about delta G again, so we're just going to say kilojoules or per mole if you have a mole of something inside of your equation. Right? And so this last thing just says, remember that a negative delta G or a positive delta E means that your reaction